All right, well, before I do that, does anybody have any questions on the quiz? The second one? Which, uh, well, what was the problem again? What is it? Yeah, it's just this. There's whatever 5 plots or whatever you just sketched. Done. No, the second one. The first one I think is. Hold on, let me see. Let me do the quiz. I got an extra one here. All right, so let's full screen. Let's do the quiz. Today's quiz. And I'll put it in the scanned notes in case you want a copy. So this one is a VDS from 0 to 5 and 1 millivolt VGS. Plot the current that flows. How much current flows in here into the gate? 0. So the only current that's flowing in the circuit's here. So you go boom, ID, VDS, and we go 0 to 5. So we go 0, and we go 1, 2, 3, 4, 5. Boom, done, 100% points. Okay, if you didn't get that and it wasn't trivial for you, you didn't pay attention or review last lecture, because I cannot go over any topic any simpler than I did, talking about turning a valve on and then watching the water flow out the hose. And if you didn't get it, you need to go review, because you know what? I'm the king of repeating myself. So I will give you the same quiz. If I find out a lot of you missed this, I'll give you the exact same quiz, or I might even put this on a test. Because if you don't know something, it doesn't mean proceed, continue on. It means you're going to be penalized. Yay. If you do know something, then I'm boring you, because I'm going to ask you the same questions over and over again. Okay? You can move that bag if you want. I don't know if it matters. All right. And on this one, it's VSG from 0 to 2. Yeah. It's just this. Well, let me ask. This is VSG. This is ID. When VSG is 0, what's the gate voltage? 2. And so what's VSG is 0? We're right here. Nothing interesting happens until VSG gets to 0.9 and the device turns on. Boom, I'm done. It literally took me 15 seconds to do this quiz. 100%. He's not challenging me. I think I'll go complain. Please, if you don't get these, go watch last lecture, because you got to understand IV curves. If I say this voltage drops and you don't understand that means the current goes up for a PMOS, that's a problem. If I say this voltage goes up and I hold a constant potential here and you don't know the current increases, that's a problem. You're not going to do well. You need to understand the MOSFETs, and I'm not asking you to know equations. I'm asking you to feel what's happening. I turn the valve on, the water increases. Don't think any deeper than that. Questions? So what would you think if Thursday I gave a quiz and I gave these exact 2 problems, plus I gave the first quiz problem? If you know what's going on, you're like, man, how can he be so easy? If you didn't understand these quizzes and you just said, well, I didn't understand, I'm used to not understanding, I'm just going to keep going on and hopefully I'll get through it. I mean, that's not going to work with me. Any questions? Any questions on last time's quiz, which I can't even remember what we talked about. Oh, it was the IV plot one. Yeah, you just got it back. Yes? Would be a diode as, I don't know. I would need to think about it, because this is VGS. So I'd take this voltage and subtract. So I think, if just without thinking too deep, when this was 0, this is 2 volts, that would be 2 volts. And if that was the gate to source, then it would be like a diode connected and I'd be pulling the gate up. Now, as I drop this voltage down, I would shut this off until it got to 0, because when this is 2, this voltage is 0. Oh wait, let me ask that. What's the voltage here? Anybody not see? Okay, when you are looking at a schematic and you see a voltage source to ground and somebody asks you what the voltage is at that node, you do not expend brain power. Your brain locks in 2 volts, and if they argue with you, you point to there's a voltage source connected to the node. Okay? When I see plus minus, if this is 2 volts, that means I'm dropping in potential. Means I'm going downhill. That means if this is 2 volts, this is 0. So I go from 2 down 2 volts. If this was 3, then this would be minus 1. Anybody not follow that? So if this was an NMOS, where that's the drain gate source, this was 2, this was 2. What's the voltage here? 0. What's the gate source voltage if this was an NMOS? 0. That valve is off. Any questions? All right. Let's work 9 points. Any questions about anything? I don't want you to have a crappy semester and start off bad. I want you to end the semester and go, man, that was a lot of work, but at least I learned something. And I don't want you to oh, I didn't know what was going on, but that's okay. I'm going to move forward anyway, because not good. All right, before I forget, logistics, I got to travel next week. So one thing, I will not have office hours. If we need to have extra office hours, let me know and we will. Or if we need to have time to work problems on the weekend or whatever, I will. Okay. What we're going to do for the class is I have dozens of recorded videos, which is also, well, you didn't get it this semester, you can go back and look at previous semesters and review. Maybe I'm becoming a poorer teacher with age. So I already linked the videos for next week's lecture. So it's up to you to watch those. Notice same date because it was on Monday, Wednesday last week. And examples so that you can go through. And then when we come back, we haven't missed anything. Any questions? There's no class next week, Tuesday or Thursday. There is lab because Jan will be there to teach the lab. But I already have the lectures loaded, so that doesn't mean I'm cheating you out of your education. It means you watch these lectures because they're going to be very similar to the ones I'm giving now, because what am I the king of? Repeating myself. Homework. To turn in the homework that is due. And I'll say this again on Thursday if I remember. The homework that's due on Tuesday, February 2nd are these problems right here. Put those in my mailbox. On Wednesday, my TA will pick them up. Although I'm grading everything this semester, I don't want you to not have homework turned back on Tuesday when we come back. So the TA will pick the homework up next week when it's due, after it's due. So put it in my mailbox in the ECE office. Any questions? Yeah, the one by the ECE office. There is no other ECE office but in TBE B3, whatever it is. Okay? All right, so let's look at 9.6. How's the solutions in general? Good? All right, 9.6 is bad. Was there somebody's name on there? To determine the value of a small signal resistance in simulation, the circuit seen in 9.41, here, let me read it here. And unfortunately, I got to go, I think I might the week after I get back, I got to go to NASA for the college. And the meeting's on Wednesday, the 17th. And so we'll see what happens with the travel. But then I got a meeting with the Army in the same place in the afternoon. So I may end up missing those lectures, but we'll have them taped anyway. And plus, I don't do that good a job lecturing anyway. But we can always do a makeup session. Okay. So determine the value of the small signal resistance in a simulation. The circuit seen in 9.41 is used. The ratio of the test. You know what? Are we recording? Yes, we are. Okay. The ratio of the test voltage to the current that flows in the source is Vt over It is a small signal resistance. Using this circuit, determine the the value of the resistance looking into the drain of the circuit in figure 940. Where's 940? Oh, okay. And show how does the 200K resistor affect It in the simulation. Let's discuss, because this is a good one. All right. Uh, so before I go and proceed, if you say big capacitor here and you put a 1 farad, 1F, what did you do wrong? 1 farad's pretty big, right? 1F means 1 femto, or 10 to the minus 15. So if you did that, it ain't going to work, because you're not putting a big capacitor there, you're putting a teeny capacitor there. So don't put the F. Everybody follow that. Okay, and if you say, well, how would I know that? Again, you go to the end of chapter 1 when you start to have splice problems, and you go, oh, 1 mega ohm is 1 MEG, not 1 M, which is 1 milliohm. Oh, 1 farad is 1, not 1 F. 1 femto means 10 to the minus farads, etc. And I go through this list, enabling you to be successful. Okay, so for this problem, it says use the 1 micron process. So let's do it real quick and then I'll sim it. Would you rather me just answer your question with a question? Just say, why didn't you read the book? Why didn't you look at the solution? Students love that, don't they? You did? What if I can't work the problem? Uh-huh. All right, so what do I need to do first? This is what we covered last time. So let me ask, what is VGS? Anybody not see VGS is 3 volts? Again, I just asked you that voltage. V gate, V source is what? Right? So what is VG minus VS equal to? Anybody not see that? What is the current flowing down here called? What is the voltage drop across here? Yeah, you're make it easy, man. If it's not easy, you're not doing it right. What is the voltage drop? Current flowing through a resistor. Well, no, I didn't ask that. If I say that's I and that's V, and that's R, what is V equal to? No, in terms of this, just looking at IR. I just asked you what's Ohm's law. I'm not going to ask you or quiz you or do anything complicated. Stop making it hard. Okay? Everybody see. Now I'm going to ask one more time. What is the voltage drop across the 200K in terms of ID? Anybody not follow that? Is anybody confused about how a current flowing through a resistor gives a voltage drop of I times R? Okay, so what's the voltage here? 5. And then you just told me there's a voltage drop there of ID times 200K, so this is exactly what I went over at the beginning of the lecture. If I power down or I drop down a potential by that voltage drop, would everybody agree it's 5 minus the voltage drop? So what's the potential here? 5 minus ID times 200K. Questions? What is VDS? That is VDS. The source is 0. VD is this voltage. So that is VDS. Yay? Okay, in the, why did I fold that? In the notes, I'm going to call this page 2. Okay? Question? Lay it on me. No, I don't know. If I'm up 5 feet in the air and I come down 2 feet, I'm 3 feet right here. So not, I got a potential of 5 volts. I drop some voltage, whatever the voltage is here. I have to calculate that. I don't know what ID is. Yeah, if I'm on the 5th floor of a building and I come down 2 flights, then I'm on the 3rd floor. It's that simple. Okay, let's continue. I'm going to redraw this so it looks nicer on the next page. When you understand what's going on, things aren't complicated and you can explain them. Okay, I understand what's going on. All right. Is anybody bothered by the way I drew this circuit? What's that? I'm drawing it so I can put crap on this side without it mixing with the circuit. Does everybody see it's the same? So this voltage I'm going to call what? This current through here is what? What's the current through here? What's the current through here? Any questions? So I'm going to try to skip a step here because we've already covered it. What is VDS? Any questions? Would this be a good problem for Thursday? Calculate the currents that flow in this circuit, but change the voltages or the resistors. Well, he went over that in class, but I didn't study, so I'm going to miss the quiz again. Damn him, he goes over things and expects us to know them. Okay, so what is the threshold voltage for this process? How do I know that? It's in the book, in the table, or I can go to the back of the book and I look at the long channel parameters and it says threshold voltage, 1 micron, 800 millivolts. How do I know this is the process I'm using? It said so right here at the beginning of the problems. Okay. What is the KP for this process? 120 microamps. Oh, damn vitamins. All right. So, here's where it gets this is kind of challenging. First thing I need to ensure for either equation is VGS greater than the threshold voltage. Is VGS, what is VGS again? 3. Is 3 greater than 0.8? What does that mean? Means there's current flowing. Doesn't mean saturation, doesn't mean triode. It means the water's flowing in the pipe. That's what turning it on past the threshold voltage is. Yay? Okay. Now, I need to determine if it's in triode or in saturation. The way I do that is I make an assumption of one and see if it's right. How do I determine once I've calculated the current if I'm right? How do I determine it's in saturation? Yeah, VDS greater than or equal to VGS minus V threshold in, which is equal, let's go ahead and write it out. What is that equal to? VGS minus V threshold in. Anybody not follow how I got that? Yay? Okay, I'm going to assume, well, let's do it the long way. What do you want to assume, triode or saturation? I want to assume triode too, because that's what it's in, but we're going to assume saturation. Question? Oh, you can ask me too, man. I'll answer questions. Oh, okay. No, I just don't want, if you have a question, everybody else is going to have it too. All right. So I'm going to assume saturation. Okay. I can look at this circuit and go, it's going to be in triode because I've used the process a lot. And I can see this 3 volts is going to turn that device on a lot. I'm going to get a lot of water flowing. And the pressure here is going to drop across the 200K. And this is going to be at a small voltage. I know that. But we don't know that because we're learning. All right. So I'm going to assume saturation. Okay. Uh-huh. Well, it depends. If I lower the resistor to 1 ohm, then I'm not going to drop much pressure, right? Yeah, yeah. Oh, and what was the size of this device? 10 by 2. Okay, how do I proceed? I can find the current. What is the current? So I'm going to, yeah, let me write it out this first time. I don't want you to say in the teaching evaluation, which I still haven't seen last year's teaching evaluations. What a surprise. He didn't write good notes. He skipped too many steps. All right, tell me how. Plug and chug. Does anybody know what that is? I'm going to just estimate it, all right? 300 times 5, let's just say 4.84. 300 times 5. Wouldn't it be like 1.5? Yeah, 1.45 milliamps. Yeah. Does anybody not follow that? Does everybody understand how my thought process is going? Okay, so if it's 4.5 milliamps, what is the voltage drop across the resistor? Okay, so I'm going to ask a simple question. In terms of ID and 200K, what is the voltage drop across the resistor? 200K times ID. So what is that voltage drop? What's that? 294 volts? That ain't working, is it? Because milli times K is 1. 200 times 1.45 is 290. 290. Yeah, whatever. Close enough. Point is, I only got 5 volts. Can I go from the 5th floor of the building to the basement level negative 290th floor? No. I can't, well, unless I get a shovel and dig, right? So this is wrong, right? So the key point, not in saturation. Anybody not follow how I did that? Questions? So I'm going to redraw the figure on the next page, and we're going to look at it from a point of view of the um, knowing it's in Triode. And I'm going to not grade this one because I'm thinking that your 320 class wasn't up to snuff and you would need to actually know something from 320. But if I'm wrong, then you can tell me. And then what I'm going to do instead is I'm going to move this problem to homework that's due next week, and I'll grade it next week. And then you can do it, and you can verify the sim with Spice. Now, I'm doing everything, right? So if you don't do a good job and show good Spice, you're not going to get points, because if you just copy down and it's not clear you understand what's going on, then I'm not going to feel good about giving you full credit for the problem. So I'm not going to grade this one tonight. When I grade the homework, I only grade the first, whatever, however many there were, I don't even remember. Yeah, yeah. Yes, I'll add it. I'm OCD, man. Don't worry, it'll show up. I'm going to do it too. We'll sim it. Okay? All right. I don't want you to say he's unfair. You guys are going to get sick of my sense of, well, you probably already are that have taken classes from me already. All right. Oh, wait, he moved the voltage source to the other side. Don't matter. Okay. So if I apply, okay, we're going to do something in a moment called small signal analysis. When Spice does small signal analysis, or we do small signal analysis, we assume the signals are small. However, so we replace the models with linear R's and C's and what have you, all right? In Spice, they replace, when you do a small signal or AC analysis, they replace the devices with their small signal model. In about 10 minutes, you'll feel better about small signal models. Spice doesn't look at the actual amplitudes that you use after you replace the devices with small signal models. So if we calculate the resistance of this device as 1K, and we put 1,000,000 volts in over here, when I do an AC analysis, Spice isn't going to know that 1,000,000 volts will move this into saturation part of the time, because it moves it up on the curve because VDS. It's still going to assume it's small. Okay, so I'll come back to that in a minute. If you didn't follow that, that's fine. I want to ask you some fundamental questions. If I do an AC signal, if I look at AC currents, and I ask, what is the AC voltage there? 0. Does everybody understand that? In fact, I can use superposition and short out the voltage source and open up the current sources. But when I do my analysis, I'm going to short this voltage source out because I can never, ever change that voltage. It is AC ground. And so when I do an AC circuit, I'm going to replace that DC voltage source with a connection to ground, because I can't change the voltage there. Now, when I look at the overall circuit, I'll have a DC voltage of 5, and then I'll have some AC current that's flowing. So if I do an AC circuit, and I don't have that resistor or that MOSFET there, and I ask you, what are the AC voltages in this circuit? What is the AC voltage there? I just asked you that. It's 0. What is the AC voltage there with a 1 volt input? 1. If this capacitor is big, that means it doesn't charge or discharge. Both sides move at the same value. In other words, I think of this as a wire. What's the voltage there for AC? 1. Well, if I've got 1 volt here, what's the current that flows? Oh, wait, he drew the current flowing up. Why did he do that? Let's do it both ways. So he did plus minus. The voltage here is what? 1. What's the voltage here? 0. Wait, it's 5. No, we're talking AC. It's 0. So what's this current ID that flows? 1 over 200K or 5 microamps. Anybody not follow that? I want to flip it around. I'm going to stop here before we go to the MOSFET part and do the sim on this. If I define the current going this way, or I ask you what the current going this way is, so I have the following. Notice when I go to AC, I use lowercase I, uppercase D. Or we'll just say I right now, right? We'll call this current flowing here, we'll call IX. And that's equal to IX, and then the DC current that flows is IX. What's the DC current flowing in that capacitor? 0. DC current doesn't flow in a capacitor, only AC. Okay, I got to change the voltage on both sides of the cap to get a current flowing through it. I'm going to write the AC as lowercase I, lowercase subscript, DC as uppercase I, uppercase X, and then I write the sum as the following, lowercase and then uppercase. And who's coming to town on February 5th? There you go. Did you know that? Yeah. Okay, any questions? Did anybody know that? Oh, man. Okay, so this is AC plus DC. This is uppercase X in case you can't tell. Okay, so let's go and finish this. If this, what is the voltage here in this circuit? What is this voltage? And what is this one? So what is the current? Well, let's see. 0 minus 1 is equal to V, and that's divided by R, and that's equal to I. So I always come back to that. That's in my brain. So if I flip one of these variables around, I know it's negative, and I just flip it back and call it minus. And what is that equal to? Minus, in this case, 200K. Minus 5 microamps. So if I define the current going down, then the current that flows is minus 5. Questions? It's all clear, right? So let's do the sim. Where are we? Boom. This is lecture 3. Is anybody using these? No? All right. Is anybody using the videos? Because hauling this crap around. You are? Is the quiz grade going to reflect that? Everybody's like, is he joking? Yes, I'm joking. All right, so let's call this value 5. Let's call this VDD. Voltage sources have to start with a V. Let's zoom out a little bit. Move this up. Grab the resistor. Just a name. You want me to call it something different? How about I call it VU and LV? I mean, why is anybody called anything? I don't know. And this value is 200K. And then let's go ahead and get the scissors out here and just ground that terminal so I can do this step by step. And this device was a 2 by 10. And then let's get the old copy out here and run it over. And this was 3. And would it be okay if I called this VGS? because I want it to correspond to what the actual voltage is in the circuit. And then last but not least, what do I need? Whoops. How do I rotate it right now? Control R. And let's do this. And then let's make this 1 farad. Oh, that's right. I just told you not to do that. Boy, I need to take my own medicine there. Okay. What am I the king of? That's right. And let's go over here. And let's go advanced. And does it matter, since I'm going to do an AC analysis, that I set the DC value here? It doesn't matter, but you know what? I don't like it, so I'm not going to use it. We'll just put it at 0. And I put 1 because in an AC analysis, the amplitude doesn't matter. And using 1 volt, because it replaces an AC analysis, it replaces all the active devices. What's an active device? Transistor, a MOSFET, with its equivalent resistances and capacitances and voltage control current sources and all that. The linear stuff that you learned. Okay, and then I'm going to right click here. And I'm going to say decade. And what does 1 decade? What's 1 hertz? What's 1 decade above 1 hertz? 10. Decade means multiply by 10 or divide by 10. That's all it means. Okay, so I'm going to start. Let's put number of points per decade. How about 100? Start frequency 1 hertz. Stop frequency a kilohertz. Or why don't we do something in mid-band? Let's go 1K to 1 megahertz. Yeah, this one might work. Some of them work okay with M, some don't. All right, any questions on this circuit? What's that? Yeah, I'm going to leave the transistor out just to show I get 5 microamps flowing through here. Okay, so I hit run. First, I'm going to show the magnitude of the voltage here for AC. What is it? 0. Is that 0? Minus 390 dB is what? 0.000000001. Everybody follow? I can't get 0 when I take a log, so it puts whatever the numerical error is in there. But I don't like that. That confuses me. So I'm going to right click, I'm going to left click here and go to linear. Boom, there it is. 0 volts. What's the AC voltage at the gate? Nobody's going to come up to me and go, I don't understand. You have a 3-volt source there and you're showing 0. My sim's not working. This is an AC sim. If I want to see the DC, I go change the sim to a DC sim. Then I can see the DC. Boom. Also 0. Now I want to see if my assumption this capacitor's big is correct. So what do I get here when I probe this node? 1. What do I get here if the capacitor's a big? 1. Everybody see that? If I see, I've got a bunch of nodes, I haven't labeled them. If I want to get rid of everything and only plot the one node, I double click. If I want to see the current through the resistor, what do? I go here and it shows me the direction. What do I expect to see? -5, right? Because I got 1 volt there AC. So I click on that. And it is showing -5. How do I know it's -5? Here's the phase shift. Remember, it's AC. It's 180. Here's the magnitude. It's 5. Does that make sense? Of course, if I define the current flowing the other way, then it's +5, just like I said with 0 degrees phase shift. Yes. That's the phase. Yeah, so let me pull that up. And I asked the Oh, you can't see it in this one. But I asked the author if he could make that dotted line thicker. And apparently there's no way to do that. Mike Engelhart, the guy that wrote LT Spice. Someday I'll wear my LT Spice t-shirt in. Any questions on this problem? Is it making sense? Okay, so now I know whatever the resistance is down here will be in parallel with this 200K because this resistance is connected to AC ground. The resistance down here through the MOSFET is connected to AC ground, so the two resistors will be in parallel. Does everybody see that? Questions? Let's go ahead and save this so it pops up when you sim. Close that. Hey, it didn't make the little error this time. Yay. Come over here. Then let's go back and think about something before I write the next page. If I look at the IV curves of a MOSFET, which we just had on a quiz, and I plot ID versus VDS, what region am I in from the calculations? I'm in Triode. So I start to draw the MOSFET curve for VGS. What does VGS equal when I draw the curve for this MOSFET? 3. Where am I in these curves? In here. Well, wait a sec. First day of class, what did we say that looks like? What does the MOSFET look like? A resistor. The slope is 1 over R. So I can replace this device with a resistance, which I'm going to call R channel. I just need to figure out how to calculate that resistance. Questions? Okay, so let's do this. I'm going to pause from that example and we're going to calculate the small signal resistance of the MOSFET operating in Triode. The way I'm going to do this, just in generic terms, this is the resistance between drain and source. So my MOSFET, and you're going to do this problem again, and it's due on Tuesday. So you're going to get good grade. So this is the drain, this is the source. I'm going to replace that with a resistor called R channel. Everybody follow? So here's what I'm going to do. I'm going to take and I'm going to bias, because whenever I do small signal resistances, I have to bias the transistor up. I'm going to call this VGS. I'm going to put a little wiggle here called VDS. Notice how I'm changing the variables. I'm going to put a bias. And I want to, before I go on, I want to discuss what's happening here. So this is this we'll say is ID, VDS, and I'm operating in the curve here. And so I'm right here, right? Everybody cool with that? So I'm operating in the triode region and I've got some current flowing. So let me explain now in terms of my house. I turn my valve on. Someone in the street starts increasing the water pressure till I get to the point where the city water is still limiting how much water that flows in the device. Now I'm going to stand in the street and I'm going to take the valve and I'm going to wiggle that valve back and forth. When I turn the valve in the street back and forth, what happens? The water flowing in the valve is going to change, right? I'm in the street and I'm turning the valve left, right, a small amount compared to this. I'm going to change it a small amount back and forth on this curve. Does everybody follow? Okay, I'm going to call that little change VDS. That's my wiggling back and forth. When I move up to this point, I'm going to call this point VDS. So I turn the valve on in the street, one full turn. That gets some water flowing. Then I go back and I start changing it 1/10 of a turn. So I just change it 1/10 of a turn back and forth, back and forth. And then I look that when I turn it one full turn, I get some DC water flow. Then when I start changing it back and forth, I get some variation, which I'm going to call ID. everybody follow how easy this is. I turn the valve on just enough to stay in the triode region, so the water at the street is limiting how much water, not the valve. I'm not out here in the saturation. Then I wiggle the valve back and forth, VDS, and measure the current that flows. Then I say, okay, our channel is 1 over the slope. What is the slope? This wiggle back and forth is ID. That's this axis. And the run is VDS, and our channel is 1 over the slope. Everybody follow? Questions? Now I got to calculate it, right? Does everybody understand what I'm doing? So now when I change the pressure, if I know the channel resistance, I know how much water is going to flow. In other words, if I know the channel resistance and I know apply a voltage, I'll know how much current flows. So how do I find the slope of the line at this point? Yeah, I get to take the derivative, right? So if I ask, what is VGS? It's for the AC it's 0, for the DC it's some value to turn the valve on in the house. If I ask what is VDS, it's the sum of these two. So on the next page, I'm going to write that ID is equal to Kp sub n times W over L times VGS minus V threshold n times VDS plus little vds minus VDS plus little vds over 2. And this is squared. Okay, wait a sec. What is this? You're confusing me. What is this thing here? That's the overall VDS, right? That's the AC plus the DC. Questions? And then I know the channel resistance is the derivative. Does everybody see the different notation? So what is VDS equal to? Yay? What is the channel resistance? It's the change in ID with respect to VDS at a point where ID is constant, where the DC is constant, and the VDS is constant. Nope, VDS constant. It's the slope. Yeah, it's at this line right here where the DC is constant and the DC current is constant, and then I just wiggle it. Questions? So now I take the derivative. And what is the derivative? What is this in terms of VDS? This term? Does everybody see this term is here? This term is here. So I'm taking the derivative of a constant times the variable. So this is x. So the derivative of this constant with respect to x, if this is x, is what is the derivative of this first part? Now I'm cringing. What's the derivative of x with respect to x of k times x equal to? 1. How about this? We'll give it to you. This is 1. dx is 1. Does everybody agree? So what's the derivative of, with respect to VDX, of this first part? Anybody question that? What's the derivative of x squared over 2 with respect to x? Yeah, just X. VDS plus VDS. Okay, so that's our channel resistance, which I'll write. But what did I assume? I assumed that this VDS was much, much smaller than VDS. In other words, I turn the valve on a lot and then I wiggle a small amount. So this term right here is approximately VDS. And when I make that assumption, what's that called? And now you know why small signals, because they only work with small signals and you're linearizing around a point. So I'm going to rewrite this as our channel, and then we'll use it and finish the example, is equal to 1 over Kp W over L times VGS minus V threshold N minus VDS. Okay, since we're running out of time, notice that it's very common when you're deep in the triode region for the VDS to be much, much smaller than VGS. So let me write that on the next page. Let's write it nice and neat. So our channel, wait, how did I get 1 over this? Yeah, it's just the reciprocal. Our channel is equal to 1 over Kp times W over L times VGS minus V threshold N minus VDS, which is approximately 1 over Kp times W over L times VGS minus V threshold N, when VDS is much, much less than VGS minus V threshold N. What do we call that? What region is the device operating when VDS is greater than VGS minus V threshold N? Saturation. And if we're less than, we're in triode. If we're much, much less than, where VDS is tiny, then we're deep in the triode region, which means we move closer and closer to the origin where VDS goes to 0. So let's go back now and look at our MOSFET circuit. I'm going to use this approximation to replace the 200K and the MOSFET channel resistance. My pen's dying, you see why I ordered new ones. So our channel then, using these values, is equal to 1 over 120 micro times 5 times 2.2. Someone with a calculator, would you let me know what that is? 600, 800 ohms? Okay, 800 ohms. Is everybody cool with that? Okay, 847. What is it? I need a reliable calculator person. Yeah, okay, 600 times 2 is 1.2 milli, times 0.2 is another, so 1.32. 1 over 1.32 is 757. Okay, so let me simplify the circuit, because I want to cover one more topic before we leave today. What'd you say, 758. See, if I had PowerPoint, we wouldn't need to do these calculations, and I know that's what you guys want. So there I go. That's my 5 volts AC ground. And so does the 200K come into play? Well, little, but practically no, because 200K is, like 100 times bigger than 750 or way more than that, right? So it's approximately 758. So the answer is no, the 200K doesn't come into play because it's much, much larger than the channel resistance. Now I'm going to verify this. I apply my 1 volt, and so what do I expect the current to flow there to be? 1 over 758. Am I losing everybody? Okay, so what's the exact resistance looking this way? 200K in parallel with 758. Does it make you happy if I draw this in parallel? This is the same potential as this. This is the same potential for both. They're in parallel. 758. So what's 1 over 758? So I equals 1.3 milliamps. It's going to be approximate. We'll simulate it right now. Any questions? So let's go back. Oh, there we go. That's because you probably had one femto here, because if you have one femto, you get zero current. So when you divide 1 by 0, you get huge, yeah. You know, I should have written that in my book. Oh, wait, I did. Okay. Bring your books next time. We might have a quiz out of the book. We'll see. Okay, does that look right? Oops, before I forget, file, save as, example 2. You should always bring your books. I shouldn't have to say that. Any questions? And what do I expect the current to be? And there will be a quiz on Thursday because I won't be here next week, and so we won't have a quiz. Bummer, eh? All right, so we hit run. And then I can look at the current through here. Does it change? Do I expect the current through the 200K to change? Of course not. I still have 1 volt here. I plot the current through the MOSFET here. And let's double click so I can see, and it's 1.17. What did I calculate? 1.13. Well, that's very close, I would say. And then I calculate what the overall current is. If I want the current to flow in the right direction, what do? Flip the capacitor around, but I'm not going to worry about it right now. And there's my overall current. Any questions? Do you see how? And I could go through and look at that. See, I'm at 20 millivolts. See at the bottom? That's my VDS. So 20 millivolts, saying it's much, much less than 2.2, so that I can make this approximation right here, is very reasonable. 20 millivolts, much, much less than 2.2. One last topic. Any questions on this? Yes? Yeah. You just go like this and go attach cursor and attach 1 or 2. Say OK, then you go drag it where you want. And then you could pull up this and say, oh, it's this at this. All right, let's go save this. Boom, save this, save. And then I want to cover one more quick topic, and then we'll pick this up at the beginning of lecture next time. And that is, we just varied VDS, right? But more common is to vary the VGS. So more common is to do the following. We apply our pressure, VDS. We operate in the saturation region. Does it matter the order that I use here? Could I put the DC up here and the AC down? Of course. And in LT Spice, I can put it as one source and specify the AC and the DC for the one source. And I ask you, assuming VDS is large, so I'm operating in saturation, please don't make me cry here. Sketch the ID versus VGS. Yeah, it just does this. Boom. Does everybody agree? Yeah. This one? No, you can't. You could, but it's not, because VDD is that, like, goes through a resistor, whatever, it's the power for the circuit. So like if you do digital, VDD is what they'll call the power for the chip. So then that goes through resistor or whatever. Okay, in this case I could call it VDD because I don't have anything, but it's more technically correct to call it VDS. Don't get hung up on the names unless it's directly between the drain and the source, then it is VDS and you can't change it. But I mean, you could call it. Yeah. Yep. I could call it VDD and it would be VDD is VDD equals VDS. Okay, so if I increase this VG, I'm looking at the clock because I hate it when professors go over. It makes me angry, and I hate it when they show up late. Yeah, that's VGS. So if I do that, I get this. Now, if I bias at VGS, then I'm right here. If I wiggle this voltage back and forth, I get some ID. The slope of this line I'm going to call GM, or the transconductance. And I can write GM is equal to GM times VGS equals ID, because this is the slope of the line. It's ID over VGS. And let's pause right there and we'll pick it up next time. So read the chapter, read the book, etc. And ask questions if you have any. Have a good day. We'll see you either tomorrow or on Thursday.